Okay, I think that we should start now. I'm sorry for a little bit late, but let's see. So last time we talked about matrix factorization. Okay, so it means we want to factor, we want to split the matrix in terms of two matrices. Similarly, for like the polynomial factorization, you want something like this expression equal to the two of these two. So you're familiar with factor. You want to factor this polynomial. It means you want to do something of the two multiplied together and you get this polynomial. Okay. So for the matrix factorization mean the same thing, similar way. Okay. You want your original matrix is written in terms of two matrix multiplication. You have one is called the L, which is called lower triangular matrix, time matrix U, which is upper triangular matrix. Okay, so you said, oh, okay, you might think that why you have to make yourself more difficult. But I explained to you here only 2 by 2 matrix, and we can do with 3 by 3 matrix, and we can enlarge it. We can make it for big matrix, okay? And you might think that why we have to deal with the big matrix, okay? And I think that there are so many applications that use the large matrix, okay? So I think that I should, because they have some student came and talked to me that why we have to bother with the large matrix. So I think that this would be a good idea that I can show you and give you some motivation, and that in the real world, in the real life, nowadays we end up solving the big matrix. That today I will show you on the TED Talk, okay? So TED Talk, this professor, um, Margot Garrison, okay? She's the, will show you, I will skip some part, okay? That the linear algebra that we learned, so the beauty I see in algebra here means linear algebra, okay? That we actually the topic here, okay, is the part of the subject called linear algebra, which we will learn, okay, for this second half for the final exam. The topic here or the subject here that we learn is called the linear algebra, okay. Algebra include plus, minus, multiplication, dividing. So here we will see how
put it take back. For sure, the algebra. And that's probably the last thing that you wanted to give it a today. Maybe you remember in algebra class that you learned how to solve small system equations and variables x, y, and z. And maybe they didn't tell you exactly what these x, y, and z were. And you were left with the impression that these equations were not particularly interesting nor particularly beautiful. But actually, equations like this are at the very core of science and engineering, and all the algebra around. And because each of these equations defines the relationship between these variables x, y, and z, and relationships and connections are all around us. Now, for that reason, we love them, and I want to share some of that love with you today. Now, maybe you remember how to solve these equations. You express most of these variables in terms of one other, q, y, and after some manipulations, you get a final equation for y that you can then solve that gives you back x and then z. Now, that works really well for these small system of equations, but perhaps you had these nightmares of going into class one day, your teacher writing down on the board this text equation and saying, go ahead and solve it. Now, the equations that I work with is thousands, if not millions of variables. And obviously, we would need a really thick piece of paper and a lot of patience to solve the way you were taught. So, of course, we don't. Instead, we use computer programs. Now, before we can use these computer programs, though, we need to reorder these equations a little bit. So we're gonna write them really, really neatly under each other. And where the variables are missing, for example, see in that first equation, we add it, but we multiply it with a 0. And then we explicitly write all the coefficients in front of it and write everything in terms of additions like this. And it seems a little bit silly, why would you do that? But now you see every equation looks the same. Something times x, but something times y, so something times z is something else. And so we don't have to write x, y, and z all the time. We just remember the order in which they occur, right? And we store these x, y, and z in a little skinny table that we call a vector, like this. And then we store these coefficients, the ones, the zeros, and here also the minus 1, in a separate table, like as I will show you in a minute here. Okay. So now the system of equations that I have is really just a table of coefficients, like this, and then this little vector with all these unknowns. Now this table of coefficients we call the matrix. And the matrix is so famous, they even made a few movies after it. And like Morpheus says in this movie, the matrix is everywhere. It's all around us, even now in this world room. So I want to give you a few examples of where matrices occur. And as first example, I'm going to take you to the San Francisco Bay. So here in the San Francisco Bay, some of my colleagues designed a really nice computer simulation of the tidal flows going in and out of the bay. And this is a really interesting simulation. It will show you, for example, salinity gradients in the bay, or maybe surface velocities that are good and useful for the American stuff. This is actually what they did last year. Now, the flow is much too complex to understand and compute the velocity in every single point. So instead, we're going to be computing the velocities in a set of points distributed throughout the domain, and here the points are the vertices of these variables. Now, through the laws of physics, we can relate the velocity in each of these vertices to velocities in neighboring points. There's a relationship between them. If there's a relationship, there must be an equation, and if I have a whole bunch of these equations, what do I get? The matrix. Now, if I write down this matrix, it would be extremely large, and we have lots of numbers in it, so I don't do that. Instead, for every non-zero in this matrix, I put a little blue dot. Okay? And then what I get is a matrix like this that you can actually look at from afar, and you can see structures. Now, we use computer programs to create matrices like this, or visual matrices like this, and these are called spy plots. And sometimes these computer programs, they have little Easter eggs in them. And so one of these programs, we type the command spy. You see, it's now we can do the same thing in your body. I didn't know if you realized this, but your body has matrices. And now I'm going to take you to the simulation that my coach of mine used to say, Diego, blood flow through your aorta. Now, this blood flow model just created using CT scanning, the aorta itself. Okay, and besides the blood flow, it will also give you really interesting information about wall shear stresses that are important for blood clotting that you want to know about for bypass operations. And again, the velocities and the wall shear stress are computed in points distributed like this. And the matrix that comes out has a really interesting structure too. Now, search engines use matrices that tell them which words occur in which websites. And I'm going to take 4 randomly chosen words: Stanford, eating, cow, and the word egg. Right? And 5 websites that have one or more of these words in them. Okay, and so there's a website of cooking or TEDx Stanford, the Berkeley website. Now, what a search engine does is creates a beautiful table where each row of the table corresponds to a word, and each column of the table corresponds to a web page. And if a word occurs in the web page, then you put a little 1, and if it doesn't, you put a 0. And what do you get out of this? A matrix. Now, in reality, these matrices are billions of web pages long and millions of words deep. And you need to be a pretty good mathematician in order to build a good search engine. So, hey, you know now that it's a good fit to be in. I want to earn a little bit of money. Well, here are those matrices. Now, the variation on this theme is shown in the next slide in the matrix. And here, every column and every row corresponds to a text document, and there is a little blue dot if these two documents have a lot of words in common. So this is a connection matrix with 20,000 documents for classes. We could do the same with web pages. Web pages, both along the rows and the columns, and put a little blue dot if there is a hyperlink from one web page to another. And what we're looking at here now is the Stanford and Berkeley web domains. With Stanford nicely clustered, Berkeley nicely clustered, but there's communication between these two because there are some blue dots on the other side as well, which is actually kind of surprising since we keep eating them. But they still want to communicate with us. Now, matrices are also in your brain. Here you're looking at white matter fibers that connect gray matter regions in your brain. And looking at this, I could create a matrix that has gray matter regions in your brain along the rows and the columns and show connectivity between these regions. So you can stare at this matrix for a long time and understand how your brain is all connected up.
Just like that, every kind of that. So you can follow what you want, but also think about that.
So it's small, so I think it's. You know, it's not so bad, and outside, but like.
So this is like
This is not the
the
people.
model system of equations, they're in your brain, they're in the search engine. And as mathematicians, we work with them daily and we really master them. And these matrices, they have personalities for us. So when I prepared for the school, I asked all my student bodies to take the matrices, and here are a couple that I wanted to share with you. So we have some matrices that are stars, we want zeros, and then in the top right, the matrices that are symmetric. And symmetry, as you know, is always signifying beauty, so we love those. And then the matrices that are symmetric and stars and are sort of banded like this, they're really fantastic. And then there are other matrices which are really like sort of blocky structures. But the very winner of this competition was the matrix called the Tompkins matrix. And that comes out a lot in signal processing, and the matrix looks like much to you, but every diagonal in this matrix has a constant number, and it makes it much easier to work with. Now, what about the next matrices? And here is the one that we take note. And there are two elements that are very different in size, and this is really hard to work with. We call it field condition. But the worst matrices that in the forward are very, very, very large matrices that are in condition. And enable to work with those, we need to write specialized computer programs. So there are millions of lines of codes everywhere that the people wrote in order to manipulate these very large matrices. For example, the matrix you heard about this morning for time models, it's very nasty matrix 3. And these lines of code, they are behind a lot of the simulation tools that you will see out there if we use science and engineering. Now, I said I was going to talk about the beauty of math, and maybe so far you're not super excited to see, well, let's see some blue dots on the screen that's not very beautiful. So let me show you how to put beauty into mathematics and algebra. Here's the matrix, and we'll associate a number with each row and column, 1 through 4. And every number is not going to be related to a node or a little ball. It's going to be small, 1, 2, 3, 4. And now, whenever I have a non-zero in the matrix, for example, like positions, in the first row, positions 1 and 3, it means there's a connection between 1 and 1 and 1 and 3. And 1 and 1 doesn't show up, 1 and 3 are. The next row gives me a connection between 2 and 4. Next row gives me an additional connection between 3 and 4. And now I draw a connection with the last one between 1 and 4. Now we have a little graph that comes out, and that looks much more pleasing than just a table with numbers. But you definitely see some shallow water models as sugar is follows as well. The standard way. And rely on them. Analog circuits, experience. Time flow models. My very favorite one. for the galaxy that tells you how the catalogs and soft catalogs lie with progress of the next step. So that math that you learned at high school, these equations you didn't like so much, that's behind everything. It's beautiful, it's omnipresent, it's everything. And we need to make such predictions. Thanks very much.
Okay, so I hope that this video will give you some impression of what we try to do. Okay, so we're dealing with the large matrix. So, but this is the algorithms. So this help people around the world to, this is just the basic things, okay? That help people around the world to understand the nature and everything, okay? So this is, I think that since I turned on the video, one other things that I want to just show you about the new modern, like even the animation movie, you know, that is the mathematics inside. Have you heard about it? Mathematics for the movie animation, okay? Frozen, and what is the girl with the curly hair? I can't remember the name. Let me just search for you, okay? Gone through the, but professor is the mathematics. His work in Pixar. Pixar movie. Oh, Pixar. Ah. Just this professor.
This is Pixar Studios. I'm sure almost everyone's heard of them and watched their movies. They've won a few awards along the way too. But less people realise just how much mathematics and science goes into animating these films. Even the boss here is a computer scientist. This is Tony Rose, and he leads the research group at Pixar. And today he's talking to us here at Number 5.
Well, my particular area of interest is in the geometric model, creating shapes and things. And that problem comes up a lot around here because you've got characters with pretty complicated shapes. Some of the characters on the board behind me. This is a sculpture of the hand of Jerry from Jerry's Game, a character in a short film we did quite a few years ago now. And it's a complicated shape, and we needed to develop some way of representing these kind of shapes in a way that artists could deal with, but computers could render and display quickly as well. So Jan Peter, the director of Jerry's Game, is also a sculptor. So he created a sculpture of Jerry's hand, and then we really digitized it and made the final surface that appeared on the screen. Let's simplify first, and we'll get back to surfaces in 2 dimensions. Let's start, say, with curves in 2 dimensions to explain the basis of the process. So what I've got here is a little 4-point polygon, and it's going to be my job to make a smooth curve out of it. I'm going to make a smooth curve out of it by just repeating a few simple steps. So the first step, I'm going to call split. And what that does is it adds midpoints to the edges. So now I've got 8 points, but it's not really getting smoother. Next thing I'm going to do is I'm going to make it a little bit smoother by repositioning all of those points. So this guy, for instance, is going to move from where he is now to a midpoint of his right neighbor. Similarly, this guy is going to move to his right neighbor. And kind of make that for you. I'll call that the averaging step. So now I've got 8 points, a little bit smoother. And again, my goal is to make a smooth curve. So I'm just going to repeat. Split and average. Now I've got 16 points to get a little bit smoother. I'll put those 2 steps into a combined step I'll call subdivide. And you see that as I continue to subdivide, the smooth curve starts to emerge. And that's the basis of how we create all of our surfaces. This splitting and averaging idea also works for surfaces. So here's an example where I start with Q. So if I split, it's a little more complicated for surfaces to split. I have to insert edge midpoints like this one. And I also have to introduce the middles of faces. But again, that's just done by average. So this point here is just the average of the points. is split followed by average. This is actually this, for instance.
Let's see.
Yeah, the purpose is this Pascal's triangle pattern doesn't work anymore. You have to use a different set of mathematical tools to figure out weights that are gonna generate smooth objects in the limit. And those are very carefully chosen weights. They were first discovered by Ed Cap 40 years ago, as the president of Pixar.
Do we know, are those like, are they like a fraction of it, what numbers are they? 1.7, 3.92 or?
Well, I don't think it,
Yeah.
yeah, the location, 1, 2, 1 means over 2, and into super zero, that's averaging things. If you work out the algebra and splitting and averaging, it's the one.
So I just want you to get the impression of whatever you do, everything surround us, okay? Even like in animation, if you have the basic background, okay? So even in the industry, in the maybe movie, they hired my professor. But he's doing the mathematical modeling for the wave phenomena. He do how to generate the wave that make the movie look more realistic. Okay, so it's used the mathematical modeling, so make everything look so nice and smooth. And even like this one, they use the algebra geometry to do all of these things. Use the math knowledge. You do the calculation, it's just mathematics, okay? So even it's the simple math, but here is more advanced or kind level, okay? Even like you see the word B-spline. So actually we have gone through when we do the interpolation. I talk about the spline function, and the B-spline is more advanced, just a little bit higher level from what we learned, but this is also the things. This one they make the movie move, and the other movie is the, let's see, what's the movie name that have the Anna Elsa? Let's see, Elsa. Let's see. They do the animation for the when they're throwing the ice, you know. I can't remember. Let's see. Oh no. Okay. Yeah. All right. I think if I find out, I will put it in the link so you guys will enjoy it for your time. At least I think that they have, and the other things that I really love it when I can't remember the lady, the girl with have the curly hair and Toy Story. We still cannot Anna, no, not Anna. Oh. Yeah, this girl from I never thought about the people will when do the hair when they run, how the curly hair move up and down. That's also using the mathematics to help produce the movement of the hand of this girl. I can't remember the name. Yeah. What's the movie in this one? I can't remember. Yeah, they're using parabolic realistic rays of even the grass and also the hair when they go up and down, like it's not just like go up and down of left or right. So they use mathematical model to do this one. And the other things like in the Frozen movie, when they throw the ice and they'll have the ice fight. And when it goes up to the roof, which has the cover by the ice, and when this fall down, the ice, the ball fall down, how the snowball break up, and how it's like, moving. So that's also the part of mathematics. It's very fun to watch it and get some idea, like when people around ask me how mathematics, why we have to learn all of these things, and at least I give you some impression of the power of mathematics, okay? That's what I'm proud of, okay? I just want to share with you, okay? So back to where we are. It's not it's not always fun like that when you work on the matrix. Okay. Now, go back to LU factorization. Okay. So for the LU factorization, imagine that we have to do the full matrix, a big, huge matrix. We try to take advantages of solving the matrix. Now, we will split that into the LU. L is the lower triangular matrix. For Mr. Doolittle. So Mr. Doolittle said that, okay, if we want to do it, I want to fix the matrix L as the unit lower triangular matrix. When we say unit, mean the element along the diagonal equal to 1. Why we have such to make this thing? Because it make life easier. People may say, why not 2? Okay. It's okay too, but you make your life harder, right? And why not 0? Because if you make this one 0, it doesn't work because you will get 0, right? When you do multiplication, if you get 0 here, you cannot get anything, you get 0. And even make this 0, you cannot get anything because this doesn't work. So 1 is the good choice, okay? So you can make it 2, you can make it 100, that's always work. It's your choice, but the easiest choice to work with is 1 because number 1 is the identity. 1 multiplied by anything is that number, okay? The identity. So Doolittle say, okay, I make it L as the unit, upper triangular matrix, okay? I will remember that Doolittle, they have L, okay? So lower triangular matrix is unit lower triangular matrix. We do this way. And the other things is Mr. Kraut. Mr. Kraut say, okay, I will do the similar thing as Mr. Doolittle, but I haven't do my research yet that Mr. Doolittle or Mr. Kraut who have done first, okay? So, but it's just give to honor these 2 guys for unit lower the names after Mr. Doolittle, and for Kraut method CROUT. Oops. คุณต้องไปทำไงเนี่ยเดี๋ยวนะมันทำไมขึ้นมาปิดเนาะใช่ไหม Okay, thank you. So, Mr. Proud, you have his name as you. Probably be the reason, I don't know, okay? They said that they want to split or factorize matrix into matrix L times matrix U. By matrix U is called unit upper triangular matrix. Okay, so they make matrix U as unit upper triangular matrix. So you will be like if you will be like this 1 0 U 1 2 1. Okay, if it's 3 by 3, you get 1 0 0 U 1 2 U 1 3 1 U 2 3 0 1 for 3 by 3, or even it's for larger. Okay, so even this crowd factorization, let's see, use the same matrix. Okay, if I want to make the cross factorization, matrix L will be L1 1 0 0, L2 1, L2 2 0, L3 1, L3 2, L3 3. But U is unit upper triangular matrix. U1 2, U1 3, U2 3. You can see that you have 3 rows and 3 columns. You have 9 elements, and you will have 9 equations, 9 unknown. Okay, by just this one, you will have 1 2 3 4 5 6 7 8 9, 9 unknowns. Okay, so you have 9 unknowns. So now you do just straightforward, do the matrix multiplication. This is 3 by 3 times 3 by 3. So the resulted matrix would be 3 by 3. Okay? Write out all those 3 by 3 elements. So the first row, first column, you get L1 1. First row, second column, okay? You will get L1 1, U1 2. First row, third column, you get L1 1, U1 3. Okay? It's easy to make a mistake. Okay, you have to be careful. Okay? 2, 2 1 here. Okay, 2 1. So it's from second row multiplied by first column. Second row, second column. It's similar, you write down L2 1 here, L2 2 here. Okay? You do multiply and then add. Okay? And then you do multiplication, L2 1, U1 3, plus L2 2, U2 3. The last row, first column, 3 3 1, and then L3 1, U1 2, plus L3 2. Last row, third column, L3 1, U1 3, L3 2, U2 3, L3 3. After you do the multiplication, third row, third column. Okay, L31, L32, L33, okay. And then matrix A equal to this matrix, right? So every element in this matrix has to be the same. Okay. Yeah. Yeah, thank you. All right. So you do this. And let's see. For this, you get L1, L11, L21, L31. Okay. Now you know L11, you will get U12. You know L11, you get U13, right? And then from this, you know, let's see. Okay, so you get this, okay, get this using this, okay. Since you know U11, you know U11, you can get U12. You will get U13. Okay, can you get U23? U33, you will get U33 when you get L22. You know L21, U12, you can solve U22. You will get U22. You will get U22. When you get U22, you will get U23. Because U21, you know, U21 is too thick here. U21, U13, you get this one. U22, you know, you will get U23. Okay. How are you guys doing it? Okay. I go to the restroom. yes โอ้ again มันจะปิดยังไงเนี่ยมันมาจากไหน all right so you guys got it L11 you get 2 minus 1 1 you get 1 U1 1 1 U2 2 is what U1 2 is 1 over 2 U1 3 is minus 3 over 2 okay because U1 1 is 2 so you get U1 2 U1 2 is 1 over 2 U1 3 is minus 3 over 2 okay I get U1 3 now to get U2 2 U2 1 is minus 1 U1 2 is 1 over 2 so you get L2 to 1 so L2 2 is 1 plus 1 over 2 right so it's 3 over 2 should I write down somewhere okay so I copy this 2 1 is minus 1 1 2 is 1 over 2 plus L2 2 equal to 1 if we that L2 2 is 1 so minus is plus 1 over 2 which is 3 over 2 okay and how about this one what is L2 1 L2 1 is minus 1 L2 1 minus 1 U1 3 is minus 3 over 2 L2 2 is 3 over 2 you can find U2 3 is that minus 1 minus is plus move to the other side minus 3 over 2 which is minus 2 minus 3 is minus 5 over 2 divided by 2 over 3 is minus 5 over 3 okay what else here okay you will get L3 too okay So L32 is 5 minus L31 U12. 5 minus L31 is 1. U12, 1/2. 9/2. This is going to be 0. And the last one is this one. What is L31? L31 is 1. U13 is first row, third column, minus 3/2. L32, L on the left, third row, second column, we just got it, is 9/2. What is U23? Second row, third column is minus 5/3. Plus L33 equal to 0. So this is minus 3/2. 3, 15/2 plus L33 equal to 0. So it's minus 18/2 is minus 9 plus L33 equal to 0. So L33 is 9. Okay. So we can multiply. You can check if you get the correct result or not, okay? Because this is very important step. Because if you factor, your factor is not correct, you cannot solve the system, okay? You cannot solve the system. Let's see, go back and copy the matrix A. Okay, let's check 2, okay, 2. This time this is 1. This time this is minus 3. The first row is done. Second row, this time this, you get minus 1/2 plus 3/2, you get 1. Minus 1. That's correct because it's minus sign here. No. So we made a mistake, right? No? We get, oh, yeah. Sorry. Second row, first column is minus 1, that's correct. Okay, I looked at the wrong. So this one, second row times second column is 1. That's correct. And then second row, third column, you get minus times minus is plus 3/2 minus 15, minus 5/2, right? Yeah. Minus 5/2 because it's 3/2 multiplied by minus 5/3. So you get minus 2. So minus 2 plus 1 is minus 1. Okay. This time this is 1. Oops. This row times this row, this column is 1. And this times this 1/2 plus 9/2, 10/2, which is 5. Okay. And then this times this, you get minus 3/2 plus 9/2 times minus 5/3 plus 9 equal to 0. Okay. Is that correct? That's correct because it's just right here. Okay. So this is, we got the correct factorization. Okay. So matrix A, if you split it or factor into two, L and U, if U is upper triangle unit, upper triangular matrix, you got this one. Okay, and if we do the Doolittle, the same matrix A can be factored in these two matrix multiplication. The difference only, this matrix is L is the unit lower triangular matrix. Okay, so it's two different factorization. Okay, two different factorization. So now, once we know how to do the factorization, why we need this? Okay, why do we need the factorization? Because if you recall what we learned at the beginning, we have a very nice structure. If we have the upper triangular matrix as the quotient matrix, upper triangular matrix, if I have U times X equal to Y equal to B, maybe. U is the upper triangular matrix. We can use the backward substitution. Right? But if we have L times X equal to B, L is the unit lower triangular matrix. So we can use what we call the forward substitution, right? And we have the algorithm for that. We have the systematic way to solve this problem. Okay, so we can try to use this two feature. Okay, so we start off with matrix A, time unknown vector, I call vector X, equal to the right hand side vector B. Okay, now if I rewrite A as L times U, so A is replaced by L times U times vector X equal to B. This is just straightforward substitution. Rewrite A as the L times U. And when we will try to think that, what is this? U times X, I will say that U, think about if U is the 2 by 2 matrix. Time X is X1, X2. Okay? For example, this is UX. This matrix is 2 by 2. This vector is 2 by 1. The resultant matrix would be 2 by 1 is the vector. I will let this one to be vector y. I call it y1 by 2, okay? And I say this is vector y. So I will say that this is my vector y. So first step, I want to find out, I solve this vector y by setting up this way. I take the quotient as the lower triangular matrix, multiply by my vector y. Is that clever? Yes, I guess. Okay. So L times y equal to B. You can use what? Forward substitution. You find y, right? You get y. And after that, you use your results from Ly equal to B, you will get to your final solution by setting up Ux equal to Y. You can use backward substitution. So for what? For X. Very smart way, okay? Because we have systematic way to find it. We know how to do this factorization. Once we factorize matrix A into L times U, you use forward substitution to get Y. And after we get Y, we solve for X by using backward substitution. Okay? Now, let's just use the Doolittle factorization. Okay, I will use the result from this one. Okay, let's see. Okay, A is this one. I copy this factorization. Now I will try to solve system A times X equal to B. Okay. Suppose I think that my F is 1, 2, 3. Okay, suppose I know the solution first. I will construct my matrix. So I have 1, 2, 3 here. 2. Okay. Suppose I have the system of equation. Let me just write down like A times X, which is X1, X2, X3 equal to -5, -2, and 11. Okay. I know that the real solution is 1, 2, 3. Okay. I hope that I'm correctly. Okay. Now, A can be split into L times U. Okay. L times U. From A, X equal to B. A is L times U, X equal to B. L times X equal to Y. So step number 1, you solve L times Y equal to B. Okay. What is L? L is 1, 0, 0. Minus 1 over 2, 0, 0. 1 over 2, 3, 0. Time y, so I call it y1, y2, y3. Equal to the right hand side vector, which is -5, -2, and 11. Okay. You get it? So you have L. L is the unit lower triangular matrix. You can find y1, y2, and y3 easily, okay? Use the forward substitution because y1 you can see that is going to be -5, right? And then -1/2 y1. Supposed to be 1, sorry. Okay, so we have 1 plus y2 equal to -2. So you find y2 is -2 minus 1/2. So you plus 1/2 times -5. What is it? -9/2, right? -4 -5 -9/2. And then the last row, 1/2 times y1 plus 3y2 plus y3 is 11. So y3 is 11 minus 1/2 times y1. y1 is -5 minus 3 times y2. y2 is -9/2. Mhm. 32 ใช่ไหม 32 16 plus 11 is 27 okay ใช่ไหม so now you get y1 y2 and y3 the next step you solve okay so this is your y right you get y1 is -5 y2 is -9/2 y3 is 27 okay now for this you have the upper triangular matrix you do it from the bottom up so you backward substitution you use backward substitution you get 9 x3 27 this give you x3 equal to 3 3/2 times x2 minus 5/2 times x3 equal to -9/2 so you can find x2 x2 is -9/2 plus 5/2 times 3 the whole thing divided by 3/2 okay divided by 3/2 is multiplied by 2/3 minus 1/2 minus หรือว่าทำไมได้ถึงสงสาร I must do something wrong. Let's check this one more time, okay? Am I right? If I think that the solution is this one, 1, 2, 3, the right hand side is this one, correct? Did you guys check?ไม่ใช่เหรอเนี่ย That's correct. -5, -2, 11. Okay. We get the solution -5 -9/2 and 27. That's correct, right? 5 minus 2, 11, yes. So my solution is correct. And what did I do wrong? Let's see. This is negative 5/2, right? No, that's 3/2 x2, correct? Minus 5/2 x3 equal to minus 9/2. Is this correct? Correct. Let's see. Minus 9/2 should be subtract by plus 5/2 times x3. Right? Yeah. Oh yeah, equal to 3. So x2 is 3 times 2/3. Yes, get 2. Oops. Okay. X2 is 2. So you'll be able to calculate x1. Now 2x1 plus 1x2 minus 3x3 equal to minus 5. So x1 is minus 5 minus 1, x2 is 2 plus 3x3, x3 is 3. The whole thing divided by 2. Minus 5, minus 2, minus 7, minus 7 plus 6. Hey, no. 9, sorry. Minus 7 plus 9. So it's 2/2 is 1. Okay, so you get x1, x2, and x3. So your homework, huh? Your homework, use the result from the Proud factorization to solve ax equal to b. A is so this system, okay? The factorization is given in class, but just try to follow the steps, but use the Proud factorization, which U is the unit upper triangular matrix, okay? Due Tuesday before class. Okay. Yeah, we'll see you guys next week, next year, next Chinese New Year, right? So.